Okay, awesome. So, right. So I thought today, since last time we saw Riemann rock and how do we get elliptic curve equation from it, and in the process of discussing Riemann rock, we ended up discussing divisors, which are a prerequisite for this. So I thought, like over the next couple of lectures, like lecture 6 and lecture 7, we can uh, discuss this elliptic curve discrete logarithm problem and some attacks on it. And some attacks on it actually require the knowledge of while pairing and sort of Tate pairing. So we can cover that in next lecture, and we can also revise in that our devices and everything we learned about elliptic curves. So let's just so this can be thought of as a like as a in this context we can study some things about elliptic curves. Right. So discrete logarithm problem. Let me state it for elliptic curve, and then the general version will be clear, sort of. So the problem is, so suppose I'm given an elliptic curve, let's say E, and it's defined over a finite field. And please recall that all finite fields are either FPs, Z mod PZ, or extensions of that. And how do we construct extensions of that? Are basically using polynomials. So any finite field uh, comes from that. So let's say it's defined over a finite field, FQ, where Q has to be power of a prime. So we are given this information, and we are also given a point P, let's say, that is that satisfies the equation of E, and it lies in the finite field. And it's of order n. By order, I simply mean, so order n here. So I'll just add a note. So order means that n times p, when I add p to itself n number of times, and this addition here is the addition on elliptic curves that we also saw. We saw explicit equations for it. That n times p is identity, and m times p is not identity for m strictly less than n. So n is sort of the smallest number, such that when we add p to itself n number of times, we get 0, and we don't get this for any smaller n. So we are given an elliptic curve defined over a field, a point of order n, and a point q that lies in this set. So p, 2p, 3p, all the way up to np. So q is basically some multiple of p. But the challenge is, so given this, find, so the challenge is to find L such that Q is equal to L times P. So why this the word discrete logarithm, where it comes from? So in the additive notation it looks like L times P, but in the multiplicative notation we can think of this. So in multiplicative notation we can think of this equation as writing Q is equal to P to the power L, and then basically taking log with respect to base P, we get this is equal to L. So L is the log. So that's where the notation discrete logarithm comes from. Anyway, so this is the challenge, that I know my elliptic curve, I know my field, I am also given a point, I know its order, but given another point Q, such that I know Q is some multiple of P. What multiple that is, this is a hard problem, and this difficulty sort of is used when some crypto systems are based on this discrete logarithm problem. So there are a bunch of attacks on this. So let's discuss a few of them. So basically the challenge is how to compute L. So first attack is, so let me see. So let's discuss some attacks on this. So first attack is Pauling-Hellman attack. And this idea is to sort of break it down prime by prime. So basically tackle this problem each prime at a time. So tackle this one prime at a time. So we are given an n which is order of p. We can write down its prime factorization. Suppose it's p1 to the power e1, p2 to the power e2, all the way up to pr to the power er. So then the fundamental idea in Pauling-Hellman strategy is to essentially compute. So fundamental idea is to compute. So we are not computing L directly, we are computing one prime at a time. So to compute L, so to compute Li's such that L is congruent to Li mod Pi to the power Ei, where I is from 1 to R. So once we have information about all the Li's, we can use Chinese remainder theorem to find L. And then use Chinese remainder theorem to find L. So how does it work in practice? Um, so we want to compute each Li. So suppose Li is equal to, so we can think of writing Li in its base P representation, like we have decimal representation, 2-adic, 3-adic, we can do it for any P. So suppose Li is, let's say, Z0 plus Z1 Pi plus Z2 Pi square all the way up to some Z e minus 1 Pi to the power Ei minus 1. So the idea is to find these Zi's and then we can find Li's. So how do we find Zi's? So this is the idea. We do it one at a time. So how do we compute Z0? So again, the idea is to compute Z's and then find Li. So let's start with Z0. How would we compute Z0? So to Let me just write computation of Z0. Computation of Z0. So we are given a point P. So let's define P0, which is N over. So let's fix a. So we have like all these PIs. Let's fix a PI. Let's just, yeah, like it will work for anything. So let me just, this I is something fixed. This is one prime at a time and then one base at a time. And by the way, these ZIs, they all lie between P minus 1 and 0, because those are the digits of base P expansion. So that's their constraint. Let me just say base P expansion. So I take n times Pi, this is an integer, and I take multiple of P by this. By that, it simply mean I add P to itself n over Pi number of times. And let me also define Q0, which is same thing, but added to Q. Now, what is order of P0? See, P0 is clearly not identity, because if P0 was identity, that would mean that P has order n over Pi. But that is not true, because we assume that the smallest number, that such that n times P0 is n is basically the order. So P0 is not identity. So order of P0 is bigger than 1. And second observation is that if I take P times P0, so P times P0 or Pi times P0 is Pi times n over Pi times P, which is basically n times P is 0. And this is, recall from group theory, that basically what we said was Lagrange's theorem, that if you have a group and you have a subgroup inside it, then the order has to be, the order of subgroup has to divide order of the group. So here we have a point such that when we add it to itself a prime number of times, we get back identity. So its order has to be 1 or that prime. Its order is not 1. So order of P0 is this prime Pi. So now if we look at Q0, this is n over Pi times Q, but Q is L times P. We don't know what is L, but it is some L times P. So it is L n over Pi times P. And now this thing inside has order P. So this in its, when we look at, so when we reduce L modulo P, we look at Li. When we look at base P expansion, since we have a point of order P, this has to be equal to the first digit. So this is Z0 times P0. Because P0 has order P. So if it's not clear, I can, so there is a step in between. So basically I'm looking at, if I reduce L modulo Pi to the power Ei, I'm looking at Li. So what is the expansion? It's Z0 plus Z1P plus da da da. Everything will be a multiple of P times P0. But P0 has order P. So P times P0 would vanish, and so will be the other term. So the only term that will survive is Z0 times P0. And now, how do I compute Z0? This is again, so to compute Z0, basically this is discrete logarithm problem, but now in a smaller group. But This is not necessarily simplifying the problem, because if I choose my n so that the primes dividing it are very large, this problem can be hard to break. So even the example that I'll discuss is for small primes, but in general, in practice, if we want to make this hard, we can choose our n. So we can choose our n so that the primes that appear in its factorization are really big. And in that case, breaking this would be really hard. So I am really curious to know what, like, how these things are really done in practice, and how are these, like, even in prime groups, how are these discrete logarithm problems solved? And there are various ways to do this, even in the context of this algorithm. But if somebody has some hands-on practice with it, that would I would be really interested to know that. Anyway, so this is for z0, and how do we proceed from here? So similarly, now the next step is to compute z1. Oh, by the way, if there are any questions, I would really encourage you to just unmute and ask, because I cannot switch between my slides and chat often. But I'll check it from time to time. But in case you have any question, just unmute and ask. That's the easiest thing to do.
So can you please go back to the top? I want to refresh my memory on the problem setup. How
Okay, this one?
um, how are we defining the LIs
How are
basically?
we defining the LIs? So the LIs, okay, so the idea is to compute. So when we look at L modulo pi to the power ei, that is that Li.
Okay.
So I'm
Uh,
computing it one prime power at a time, and then I can combine all that information using Chinese remainder theorem to find L.
oh, okay. Okay.
Okay? Yeah.
Yep. Thanks.
Because see, everything is modulo n, because n is the power of p, right? N is
Yep.
the order of p. So I only need to determine this L modulo n. So this approach works because Chinese remainder theorem. Like if we are looking at, like if we think of integers, then obviously there would be infinitely many solutions. But Chinese remainder theorem tells us that modulo n there is a unique solution, and that is
Right.
the that we're looking for. Yeah.
Okay. Thanks.
Again, as I said, like this is breaking down problems to one prime power at a time, and even more so one prime at a time, so in prime groups. But even for larger primes, this can be hard. So if somebody has some practice or hands-on experience with this, I would be really curious to know how these things work in practice. But anyway, so computation of, so the next step is computing the next digit or next base, so z1. So what we do is, similarly we proceed, we define q1. So instead of n over p, we now take n over pi square times q minus z0, which was computed earlier. So we subtract this. And now this is equal to n over pi square. Q is L times P, so I can take P out. So this is L minus Z0 times P. So L minus Z0 times N over Pi square times P. Again, if we look at this point here, this has to be of the order Pi square, because by the same logic we used, this is not of order Pi, this is not of order 1, but Pi square makes it 0. And so that's the smallest one that we get. So yeah, let me just write it. So order Pi square. So now just by doing the same thing that we did, L minus Z0 would start from Z1 times P plus z2 times, sorry, pi, z2 times pi square and everything that will, so z2 and everything after that will be a multiple of pi square, but this point is already of order pi square, so everything would vanish except z1 would survive. So it would be z1 times pi times n pi square times p, which is z1 times n over pi p, which was p0. So again, so our q1, so we can compute z1 by just doing this, so solving discrete logarithm problem here. And similarly, we proceed. So we just have to do this iteratively. Let's see an example. And this is from textbook. So this, everything I'm saying is from our textbook. But I think the more interesting examples here are would actually be something from practice or something from real life where we have large primes. And it would be nice to see how successful is this algorithm or how badly it fails. But anyway, so let's take some concrete examples. So let's say our elliptic curve is given by this equation y square equal to x cube plus 1001 times x plus 75. And let's say we are thinking this over finite field over this 7919, and our point P is 40236036. It lies on this elliptic curve and over this field. And the order of P, which we called n, it's basically order of P, is 7889, and its prime factorization is 7 cube times 23. So we have to consider two primes, and we have to do this problem for 7 and then for 23. So now let's say our point Q is 41353169, and we know that it is some multiple of P, but we don't know which one. So want to find L such that L times P is equal to Q. So let's just start one prime at a time. So first we are considering 7 cube. So let's determine L modulo 7 cube. So modulo 7 cube. So its 7-adic expansion would look something like, and let me call it L modulo 7 3. Say, let me give it a name. Let me say L7. So its sort of expansion would have 3 digits. So Z0 plus Z1 7 plus Z2 7 square. And we want to find all of them. So we just do what we discussed. So first we compute P0, which, let me go back. So P0 was essentially n over Pi times P. So n over Pi here is 7 cube times 23 by 7 times P, which is 7 square times 23 times P, which is 7801 times 2071. And again, these addition, like we saw using pen and paper, how do we derive equations from it? But I really doubt this is the way things are implemented because it would take too much time. So what are some efficient algorithms to add points on elliptic curves? That's another good question, and I would like to know if somebody has computational experience with these things. So anyway, uh, So this is P0. Q0 is same thing, but we add Q. So 7 square times 23 multiplied with Q, and this is 78012071. And let's just go back. Our Z0 was basically the discrete log of Q0 and P0. So, but here, oh, we are lucky. Q0 and P0 are same. So Q0 is equal to P0. So that gives us that our first digit is 1. So now we move a step ahead. We want to compute Z1. So Q1 was, and again, let me just go back. Q1 is this number. So n over pi square q minus z0p. So it's n over pi square would simply be 7 times 23 q minus p. We know how to add, subtract, and everything, and now, yeah, using those equations, but again, using some really fast algorithms, I'm assuming. So this is our q1. And our z1 was, so z1 satisfies this equation, and we know our p0. So z1 is 3. And again, if somebody asks me how do you actually compute z, well, z0 is trivial, but z1, I don't have a better answer than saying that let's start doing it by naive search. And then in this case we would be lucky because z1 is very, very small, so we can do it by naive search. But again, I'm just repeating this again and again because I'm really, really interested. If somebody has some computational hands-on experience with this, that would be really, it would be really good to talk about. So this is our z1. And similarly, so doing this sort of thing inductively, q2 would be, so last power of 7 would be cancelled out, and then q minus p minus 3 times 7 times p, which turns out to be 72857905. And this is basically 4 times p0. So that tells us that our last digit is 4. So our L1 essentially is 1 plus 3 times 7 plus 4 times 7 square, which we simply, yeah, it's 218. So our L is 218 modulo 7 cube. That's first information that we know. So now to finally compute L, we need to find out L modulo 23 as well. So again, same thing. So mod 23 computation. So again, we start with 23, but now we do P0 is n over P would be 7 cube. P, we find this is 71907003. Similarly, Q0 is 7 cube times Q, which is 2599 times 759. And then this P0, if we add it 10 number of times, this is Q0. And this 10 is already large. I mean, I don't want to do this addition 10 times by hand at least. But maybe the naive algorithm works for 10. So L2 is simply 10 and we are done. So because 23 is a single power, we don't need to go to other digits. So our number that we need to find, L is basically 218 modulo 7 cube, and L is 10 modulo 23. So now combine this, apply Chinese remainder theorem, and we can get that L is 4334 mod n, which was 7 cube times 23. And again, as I said, if we If we don't have this mod and constraint, then obviously there are infinitely many solutions to this. We can just keep adding multiples of n. But for our setup, we only care about things modulo n. So this is the unique solution, and this is our L. Just a refresher, Chinese remainder theorem. So how do we compute this? So there is a very neat formula for this. So I'll only talk about two congruences, and multiple congruences case follows easily. It's the same thing. So suppose we are given a system of two congruences. Suppose we know that x is a mod m and x is b mod n. And a crucial assumption for Chinese remainder theorem is that the different moduli are co-prime to each other. So GCD of m and n should be equal to 1. Otherwise, there is no guarantee that there will be a solution. Like a naive example would be like if I have x congruent to 1 mod 9 and x congruent to 2 mod 3, this obviously has no solution. So this assumption that my different moduli are co-prime to each other is very important. So if I am in this setup, the unique solution is given by this formula. So basically, if we just look at, so we want x to reduce a modulo m. So to a, I'm adding a multiple of m, but not just any multiple. I want it to reduce, yeah, not just any multiple, because when I'm looking at mod n, it should reduce to b essentially. So the multiples are chosen a bit carefully. So x is a times something plus b times something, right? But when I look at things modulo m, I should only get a. So b should be, so there should be an m here, and then there should be an n here, right? But now there is a small catch, because if I look at mod m, the second term would vanish. But then I'm left with a times n. I don't want a times n, I simply want a. So I want n to be multiplied with something so that it becomes 1, right? So let's say those numbers are y1 and y2. And how are y1 and y2 chosen? Precisely like this. So n times y1 should be congruent to 1 mod m, and m times y2 should be congruent to 1 modulo n. And why can I do this? See, because m and n are co-primes. So looking at mod m, n always has a multiplicative inverse and vice versa. So now we can quickly check. So modulo m, the other term would vanish, and this is a. And modulo n, the first term would vanish, and this is, we are left with b. So this is a solution, and this is unique modulo m times n, because yeah, we can. This is an easy verification. For more than two congruences, the same approach would work. We just have to keep track of yi's at every step. That's it. Any questions about this? Any comments? Anything? So a sort of second, so that, yeah, as I said in the beginning, there are various attacks on this. This is one. The other attack is, and this one is actually very interesting, is Pollard's row attack. So this is a bit again, will, like, there is an example given in textbook and I'll discuss that. But even in this case, I'm actually very curious to know how these things actually work out in practice, because this method almost seems, it seems so convincing, but I'm not sure how it would work for most, like how it would work for most cases, or is there a theoretical proof or a theoretical idea behind it? Anyway, so let me just restate. So we are in the setting that we are given 2 points, p and q. So p is in e f q order n, and we know that q is l times p, and we want to find l. And again, L modulo n would work essentially. So Pollard's row attack idea is to find, so it's some sort of an iterative algorithm. So the idea is to find two distinct pairs. Let me use the textbook notation so that if you go back and read it, it would be there would be no notational confusion. So two distinct pairs, let's say C prime D prime and C double prime D double prime, such that when I take C prime P plus D prime Q, this is same as C double prime P plus D double prime Q. So this is the way this algorithm works. It basically generates these pairs C prime D prime and C prime double prime using a random function, which is fixed in the beginning. So using a random function, and it just keeps repeating this till we crack this, till we land upon this kind of situation. And if we are able to find two such pairs, then we know what to do. So if this holds, then C prime minus C double prime P is equal to D double prime minus D prime Q. And now everything, let me just write modulo n because everything is happening modulo n, so to say. I mean, at this stage, it doesn't make sense because we are adding points on elliptic curves. So let me not say this. But Q is L times P. So C prime minus C double prime P is equal to D double prime minus D prime L times P, right? And we know that P has order n. So what this means is that C prime minus C double prime must be congruent to D double prime minus D prime times L modulo n. Right? This is the only way this would make sense. And now, if we compute inverse of D double prime minus D prime, so L would be given as C prime minus C double prime divided by D prime minus D prime modulo n. And when I say divide, think of inverse. So this is not really a fraction, this is an integer. Like for example, 3 inverse modulo 7, so 1 over 3 rather. So 1 over 3 modulo 7 makes sense because that's just 5. Because 3 times 5 is 15 and 15 is 1 modulo 7. So this 1 over is basically the inverse, so it will be an integer. So that's what I mean. Yeah, so this is the idea. This is an iterative algorithm. We take a random function and then we sort of generate these pairs using that function, and we just keep doing it till we crack upon such a thing. And then our L is basically easily given by this. So here are some so this is a nice observation. So an observation. So the expected time for this algorithm to finish or to terminate, it depends only on n and is approximately square root of pi n over 2. And this number is an exercise in probability. It's some sort of a, so an analog would be basically if we have a classroom, then how many children at least are there before we start observing multiple birthdays? It's that sort of a situation. So the expected time only depends on n. Again, if this n is large, this can take quite a long time to finish. But this, yeah. This algorithm is very surprising to me because I don't know what's the theoretical reason why we can always choose a random function. I guess the idea is that for most of the cases we expect this to finish in a reasonable number of time. But again, it depends on choice of function as well. So how do we actually do these things in practice would be a so let's see an example from book. It's so again. So our elliptic curve, let's say it's given by this equation, y square equal to x cube plus x plus 44. And we are thinking this over f 229. And our point P is 5 comma 116. And let's say our point Q is 155166. And our n, which is order of P, is 239. And this is a prime. So basically, the previous algorithm is not really helpful here because we are not reducing the problem. It's just, yeah, 239 is a prime and somewhat medium sized or large. Anyway, so here is the function. So, so we define the function from this set P, 2P, 3P, all the way up to NP to 1, 2, 3, 4. And this is some sort of a partition whose choice, like the size of partition is also in our control. So we can take our target set to have a bigger partition, like 8 or 16 or 32. Anyway, and this is how this is defined. So h of x comma y. So we take a point in here, we look at its x and y coordinate, and we send it to x modulo 4 plus 1. And again, in general, this is a partition function. It really depends on us. And again, we have another choice here. We sort of have to choose. So whatever is the number of partitions, like for example, here we have 4. Suppose we had 8 or 16. So then we also have to start with something, start our algorithm with something. So here is our choice of 4 triples. So first one is A1. We choose A1, B1, and then A1 times P plus B1 times Q. So if we choose our, let me write round brackets instead of square one. So if we choose our A1, B1 to be 79, 163, and we sort of form this point, it will be 135 and 117. And our second choice is 206, 19, 96, 97. Our third choice is 87, 109, 84, 62. And our fourth choice is 219, 68, 72, 134. Again, I don't have a very good explanation for how do we choose these things, because I guess it's the idea is to obviously terminate the algorithm rather quickly. So how does it depend on these choices is, I mean, how does the algorithm depend on these choices will be clear from what we'll discuss. But again, how do we make these choices in practice is really an interesting question. So now once we choose our AIs, sort of, uh, so this is the general idea of algorithm. So again, these are A2, B2, and so on. So once we make our choices, so we select some C prime and D prime modulo n, and we assign x prime as this. So now we set another variable. We assign x double prime as x, and then C double prime as C prime, D double prime as D prime. And now we sort of start doing our iterations. So this is our iteration. So we compute, let's say j is equal to h of x prime, and now our x prime becomes x prime plus rj, where rj is basically, suppose this is r1. So similarly we have r2, r3 and r4 and so on. So x prime plus rj, c prime will become c prime plus aj modulo n, and d prime will be d prime plus bj modulo n. And then we do this, we do the following step twice. So repeat this twice. So we compute j as h of x double prime. Again, sort of set x double prime equal to x double prime plus rj, c double prime as c double prime plus aj mod n, and d double prime as d double prime plus bj mod n. So we do this step number one, and we repeat this step twice, and we sort of keep doing this till we land upon our pairs c prime d prime, such that c prime d prime is equal to c prime d double prime. So for the example, what happens is, if we start doing this iteration, so in sixth iteration, so for our example, in sixth iteration, we land upon c double prime d double prime as this 192 and 24, and our point c double prime p plus d double prime q is equal to 57 comma 105. And then in 12th iteration, we sort of land upon this pair c prime d prime, two one three and 104, such that c prime p plus d prime q is essentially what we noticed before, 57 comma 105. So now basically 192, so what we have is 192 plus 24q is equal to 213p plus 104q. So now we know what to do. So we arrange the terms. 192p minus 2113p is equal to 104q minus 24q. This is just equal to minus 21p is equal to 80 times q. So now L is basically 176 mod the prime that we started with. Again, there can be, as I said, these sort of algorithms, there can be many challenges, obviously, depending on how big the prime is and how many iterations it's taking. And obviously it depends on n, and that to the power of half. So if our n is bigger, then the number of steps can be very, very large. And uh, i'm not really I'm not really good at saying that if there is any guarantee of this will actually give you the correct result. But I guess these sort of algorithms work in a way that they are expected to work most number of times. And but yeah, as I said, it would be interesting to see how good or bad it is for big primes. Maybe these things are already known, so if somebody has already worked, then it would be good to interact. Yeah. Anyway, I see there are questions. Oh, George, sorry, I got no. It's okay. It's completely fine. Um, so these are two. There are other methods also. There are other attacks. The one that is really, really like interesting in the sense interesting for our setting, basically, because I want to discuss whale pairing, so just a motivation for that. So there are something called as isomorphism attacks, and how this works is, so same setting. So let me just repeat it here because it was a couple of slides ago. So we have an elliptic curve defined over finite field, let's say fq. We have a p of order n. We have a q. We want to find L such that L times P is Q. That's our idea. Now suppose we are in a nice, suppose, let's simply, suppose N is prime. In that case, this group, so basically if we take P, 2P, 3P, all the way up to NP, we can think of this set as a group with respect to the addition that comes from elliptic curves. And not just a group, it's a cyclic group of order P. Any group of prime order has to be cyclic, because you pick any element of that group not equal to identity and take the subgroup generated by that. So we know that order of subgroup has to divide order of the group, but order of my group is already a prime. So what are the possibilities for my subgroup? It's either identity or it is the full group. So any group of prime order has to be cyclic, and any two cyclic groups are isomorphic, because when I say isomorphic, I mean a map that is bijective and it preserves the group structure. So in cyclic, for cyclic groups, there is only one thing that we have to keep track of. We have to just match our generators, and then all the other properties would follow. So there is always a unique cyclic group of any order, because we can identify all of them via group isomorphisms. So this group, which is cyclic of prime order, is isomorphic, where G is another group of order n. So let's say there is an isomorphism like psi. So if we can compute psi, then solving discrete log problem in, so basically if we can, let me say, if we can compute psi, then solving discrete log logarithm in one is basically solving the problem in the other group. So log p q, or let me so what is the advantage of computing psi? So in my first group, like the group P2, P3P, I know that Q is L times P. Now I map this, so apply psi to this. So mapping this in G, I get that psi of Q is equal to psi of LP. Now it's a group homomorphism. It's more, it's actually a group isomorphism. But group isomorphism is basically a homomorphism that is bijective. So it preserves the addition structure. So adding in first group is same as adding in second group via this map. So psi of L times P is basically L of psi P. So solving discrete log problem in first group is equivalent. And this is an isomorphism, right? So this is bijective. So I'm not really losing any information. Is equivalent to solving DLP in G. And so this can be reduced so this problem can be reduced if for some G we know algorithms that are nice and they finish quickly and everything. So one approach, so a very special case of this is suppose that GCD of my order that I started with and my Q, it's the finite field over which my elliptic curve is defined. Suppose they are co-prime. Then we can use while pairing and Tate pairing to give an isomorphism and then solve using that. So, and there are other techniques also in this direction. Like for example, there is while descent attack and various things. There are other attacks also. There are something called index calculus methods, for example. And there is a very nice survey by Professor Silverman on this that discusses why index calculus methods fail when it comes to elliptic curves. So the idea of index calculus method. So let me say here, before I discuss index calculus methods. So there are attacks using while pairing and Tate pairing, and I just wanted to give some motivation to discuss these things. So next week I want to discuss like what is whale pairing and these things sort of. So we'll discuss whale pairing and what is this isomorphism and how do we attach and what is the group and everything. We'll discuss whale pair. So just wanted to give some motivation of why do we care about these things. Anyway, so there are these other form of attacks called index calculus attacks. So the idea is to sort of have this large set of primes such that we know that in our group everything comes as a power of that, and we can solve. So to find log base is basically solving log base of those powers. But the problem when it comes to elliptic curves is that elliptic curves don't really lift nicely. So if we are looking for elliptic curves that are defined over finite fields, so its points are in a finite field. If we want to lift them over to, let's say, rational or any other characteristic zero sort of situation, these are not, it's not really easy to do them. How do we lift them? So yeah, so there is a very nice article by Professor Silverman on this. It's a survey article on why these things are challenging and when it comes to elliptic curves. So anyway, so yeah, so next week I just wanted to discuss sort of whale pairing in the context of this. If yeah, if there is an interest to see other topics, just let me know. Or if you want to discuss anything related to elliptic curves in more detail, but let me know. While pairing would also be a good opportunity to revise what we discussed last time. So divisors and everything will show up again. So that would be a good recall as well. But yeah, we can. That's it. If there are any questions, please let me know. Oh, could you give the Silverman reference? Yes, I will. Yeah, so there is a nice survey article. One second. Hellman index. Yeah. Yeah, it's called elliptic curve. And no, one second. There was supposed to be a survey article. I'm. I actually had it on my browser just an hour ago, but I think I closed it. I'm just trying to find it. I'll send the link in Google Meeting.
Yeah, thank you. Or if you don't get to it now, maybe on the Zulip channel.
Yeah, Zulip definitely, but I think I should be able to find it. Yeah, that's it. There is. Actually, I have the entire PDF. So it's basically it was a plenary talk given in 2008 in Canada, and the title is "Selected Areas in Cryptography." My guess is it's more like a collection of articles that were there in on that. But in so Silverman's is the first invited talk, and it's called "Lifting and Elliptic Curve Discrete Algorithms." Hold on, I think I can find a PDF as well. This is a so by the way, there is a complete book available if anyone is interested. So if you have access to Springer, it's right there.
Okay, thank you.
Yeah. Yeah, I think the easiest thing for me to do would be to download the PDF and basically share it on Zulip.
Is it the four faces of lifting for the elliptic curve?
I think it talks about lifting in detail and what are the issues in it. And it also gives references to other articles. So if you want to supplement.
Yeah, thank you. I find these surveys very helpful.
Yeah. Yeah, it's a survey article. Any questions? Thank you. Thank you, Stefano. So I think I can stop recording. And then if anyone has any questions, we can chat.